Today is Tuesday. We are going to be talking about homework 6 today, and we'll probably be talking about some of homework 6 next on Thursday too, presumably. Next Tuesday, there will be a reading assignment. There will be a couple papers that we'll discuss from the literature. And then next Thursday will be the first exam. So this is the last of the homework that you will be doing before the first exam, and presumably stuff from this homework will be covered on the exam, and nothing thereafter. And again, I'll remind you that I'm going to ask you to make out a sheet of paper that has written on it things you want to use for the exam. And that even though the exam will be done at home, that you only use your sheet of paper, not say your previous homeworks or your book or other sources. And I'm encouraging you to do it that way, largely to get you to write that sheet of paper. And I'd like you to send me an image of that sheet of paper that has your stuff on it a week from Thursday. And, for the most part, Thursday morning, sometime between early in the morning and 10, if you send me a sheet of paper, I'll send you an exam. And the exam will be due when you are done. I would like you to do your best to not sweat how long it takes you to work at your own pace. But if you run into a problem that makes no sense to you and that you can't figure out how to make progress on it, move on. Just say, didn't understand the problem, move on. Don't hurt yourself fighting with problems that don't make any sense. It will either click and it'll probably be easy, or it won't click and you'll miss that one. And that's okay too. Again, remember the grading is do your best, get a B, do well, get an A. And if it turns out that your best is if most of the problems don't come easily to you, except you might be getting a B in the class, it's okay. But don't hurt yourself. Don't spend days, hours agonizing over questions that you hoped you would get, but are struggling with. It's okay. Don't fight it. Just let it be. And but that's not to say that you have to do it super fast. Do it at your own pace, in your own way. But just please don't agonize and spend days. And I've literally seen students stare at problems and hit themselves in the head, trying to come on, understand it. And I don't want you to do that. If it's there, it's there, and if it's not, it's not. And move along, and it'll be fine. Other questions on any questions on exams or class format or that sort of stuff? Are we ready to talk about homework 6? If so, let's begin with Carmen with problem 1.
All right. Oh, let me share my screen. Okay. So problem 1 is 3.4 in Gillespie, which I am forgetting which one it is right now, but I'll pull it up.
So it's asking you to plot the change in the allele frequency as a function of the allele frequency for
for h equals 0.1 and h equals 0.9. So these are my graphs. But then I actually thought that might be wrong, and I made these graphs.
I think they're the same graph, aren't they?
They are the same graph. They're just slightly different equations, and I actually wasn't sure. So for the first one, it's just the pH plus Q 1 minus H. And then for the second graphs, it's the full equations of delta SP.
Yeah, I was expecting you to plot what you have on the screen right here.
Okay. Sounds
So-
good. Okay, so these are my graphs, and then it asks like what effect H has on the direction on directional selection, and I said like which like allele is favored, so like in which direction it's selecting.
So what is the scale for both graphs? Tell me about the y-axis on both graphs.
It's very small.
Yeah, but what's the sign?
Delta P.
Yeah, well, yeah. Is
The
it
change of P.
yeah? Is it positive or negative or zero?
It's a positive.
Yeah. So what does that mean then, in words?
If the change is positive, then it's increasing.
So for all values of h between 0 and 1,
P increases.
that's it. That sometimes it increases fast, sometimes it increases slow. You can see from the picture where it increases fast. You can see from the picture where it increases slow. But for all values of p, it's increasing either just a tiny bit or quite a bit in sort of the middle ranges. So h between 0 and 1, if we've normalized things so the A1 allele is most fit, means the A1 allele is increasing in frequency.
Makes sense.
Everybody clear on this? This is the first thing you guys need to learn, or at least should remember, that h anywhere in the range of 0 to 1 implies the A1 allele is increasing in frequency, and that it ultimately is going to go to 1. Cool. Up next is Mitchell with problem 2.
All right, I'll see if I can share my screen. So it was problem 3.6 in Gillespie with graphing p hat as a function of h for when h is -1 to 2. And then it was asked about like over dominance and incomplete dominance, where on the graph it would relate to, which is something I did not fully know. But when I graphed p hat, I used this equation so that it's h is in there. And then I marked on the graph that it provided where I thought over dominance and incomplete was.
Yeah. So over dominance goes all the way back to negative infinity. And,
okay.
And under dominance is that area from 1 to infinity in the other direction.
Okay.
But you are completely correct. Incomplete dominance is that this area between 0 and 1. You could probably cut off these pictures at p = 1 and p = 0, because those are not
possible.
Yep, anything outside that. And the negative side is over dominance, 0 to 1 is incomplete, and 1 above is under. And I am going to share my screen because I want to. So here is something you guys are going to know and intuit and remember and absorb, and thereafter recognize how often your colleagues use the word wrong, particularly if they're human geneticists. The word dominance talks about the heterozygote. Dominance is about heterozygotes. The word dominance describes the fitness of the heterozygote or the phenotype. That's what dominance means. Dominance is about heterozygotes. Overdominance means heterozygotes are most fit or biggest. Underdominance means heterozygotes are least fit or smallest. Partial or incomplete dominance means the heterozygote is at fitness somewhere in between the two homozygotes, or at phenotype in between. If the heterozygote has fitness exactly halfway between the two homozygotes, we call the locus additive, or we say that it has additive dominance. H is called the dominance coefficient because it determines the fitness of the heterozygote, and therefore the form of dominance going on at the locus. H is the dominance coefficient because it describes what's going on in the heterozygote. If H is 0 exactly, we say dominance is complete, and we say A1 is dominant to A2 because the heterozygote has the same fitness as the A1 homozygote. We say that A2 is recessive to A1. If H equals 1 exactly, we say dominance is complete, and A2 is dominant to A1 because the heterozygote has fitness exactly equal to the A2 homozygote. We say A1 is recessive to A2. The form of dominance determines the fate of the A1 allele. If A1 is the most fit homozygote and dominance is partial, incomplete, complete, additive, any of those, then A1 will ultimately be fixed in the population. If A2 is most fit, then dominance is partial, incomplete, complete, or additive. Ultimately, A2 will fix in the population. If the locus is overdominant, H is less than 0, then both alleles shall be maintained indefinitely at equilibrium. And if it's underdominant, then one allele or the other will be lost, depending on the precise current allele frequency. So the value of H fundamentally determines the fate of the alleles. That dominance is ultimately what is going to determine what happens, whether one of the alleles fixes, whether the other allele fixes, or whether it goes to an equilibrium. And I just have the exact same picture that Mitchell did, only I cut it off at 1 and I cut it off at 0. And this is the region of overdominance, and this is the region of underdominance. Everything in between is between.
So is this definition dependent on the fact that the allele has to have an effect on fitness, right?
Nope.
So
You'd use these same terms for phenotype.
So what would be like the classic genetics, like, Mendel's peas, wrinkly or smooth? I mean, are all those complete dominants?
Yeah. The original experiment, I can't remember which way around it was, but I think smooth was dominant to wrinkled. And as a result, 3/4, when he had a cross between what we would call heterozygotes, 3/4 of the peas came out smooth and 1/4 came out wrinkled, or vice versa. I don't remember which one was completely dominant to the other. We will discover that complete dominance is very, very rare in nature. That although nearly complete dominance may be common enough that we can approximate it with complete, that for most things, almost everything is going to be almost additive almost all the time. That hopefully by the end of this chapter, we'll even have some intuition for what we expect to show dominance and what we expect to be nearly additive. But what you will find as you spend more time with your friends is that people regularly use the word dominance to describe, say, the penetrance of an allele rather than the phenotype of a heterozygote. It's often even hard to follow what they mean when they say dominance. And they've often just literally confused the word with penetrance. And it's very peculiar. But you shall not do that. Dominance always refers to the heterozygote's phenotype or fitness. Questions? I will stop my share and we will move to problem 3 with Young Sion. Right in the middle of my screen.
Okay. Let me share my screen first. Yep. So the problem was to graph delta P versus P for an underdominant locus. And so for the underdominant locus, H would be larger than 1. So this is the plot that I made. So, and I used an arbitrary value of H, which was 1.5 here. And then from this graph, we can observe that this delta P is negative when P is between 0 and like this value, which is P hat, which would be 0.25 if I calculate with the formula in the book. So in this area, the P will be decreasing because the delta is negative. However, in this area, which is larger than the equilibrium, the P will be increasing. So when so if P is moving from this way, like moving this way from the equilibrium, the P will decrease and then go to the allele frequency of 0. And then when the P is moving this way, it will keep go toward to allele frequency of 1. So it will eventually be fixed.
That's it. That is how you should understand underdominance. There is an equilibrium frequency, and that equilibrium frequency is h minus 1 over 2h minus 1. In this case, it's at 0.25. And technically, you could stay at that frequency forever. And if your population ever moves off that frequency, if it gets a little bit less than that, then selection will, on average, decrease the allele frequency, and it will continue to decrease the allele frequency until it gets to 0. If it happens to move a little above your equilibrium frequency, selection will increase the allele frequency, and it'll increase it forever until it reaches frequency 1. So while an underdominant locus could, in principle, remain at its equilibrium frequency for a while, in practice, it's going to move a little bit up or a little bit down due to sampling, and then selection is going to push the allele frequencies one way or the other to either 0 or 1. Which is why you don't ever really expect to find underdominant loci in nature. That if it's any kind of strong selection, you imagine that at one point selection either pushed the allele frequency to 0 or it pushed the allele frequency to 1, and that it didn't let it balance there on the knife's edge for any period of time. Does that make sense to everybody? So underdominant selection. Yep, question? Sorry.
Yeah, could I just ask a question about the function for that graph? Because I think I approached it, I mean, I ended up with like a more of an asymptote situation. And so I think I just approached it with the wrong.
You want to show the formula you used, and I'll show you the formula I used?
Yeah, sure. So here is what I had. One second.
Oops,
so this was the code that I ran. Actually, it doesn't even matter what H2 is. So I used where this would be like, I think the value of P, I believe, but it ended up with a graph that looked like this.
So we were looking for the delta P formula, which
okay,
so that should have had something like a PQS.
Right, the P
H, Q, H1 minus H over W bar, or something like that.
Mm-hmm. Yeah, I think this guy probably.
Look at
which
that.
I used in my previous equation.
Yep, that looks like about the right formula to me. with
Yeah, I'd use this. So this, I mean, again, doesn't really.
Yeah.
But this ends up creating this funky thing, which I was just setting it for arbitrary values to kind of see what was going on.
so
Don't really know that my function worked, but
so P can only exist between 0 and 1.
right.
So you have, so I is not an integer here. So this is, so you're feeding in the function that looks like P1 minus PS doop dee doop. Those parentheses are probably correct. So is the stuff at the bottom. Just curve that function from 0 to 1 and see what happens.
Oh, okay. Huh. You probably just got lost in the range that I had set it.
And I have a feeling your value of H here is negative rather than positive. So what value of H are you using in this plot?
Let's find out. I am using a
Negative something.
0.01. Yeah.
Oh, oh no.
Oh no, you know what? It could be something different because I've kind of messed around with my H. So if I set it to something greater than 1,
it's equal to 2. Let's plot it again.
like 2, and then
Yep, that'll good.
okay. Yeah, this is when I started assigning the values, so it kind of is still a little bit funny, but I think I get the idea of what needs to be done.
It's still not positive 2 yet, but give it one more shot with H equals positive 2 and you'll get that picture. I guarantee you.
Sure. Yeah, I think I just wanted to understand because I clearly had used the incorrect for this particular problem. So, okay, thank you.
No worries. Kevin is driving a moving van across country, so he will not be joining us. Up next with the next problem is Liana, which is problem, what are we on? 4, I think.
Sorry, did you say Linnea or Kiana?
Yeah, sorry. I'm probably pronouncing it wrong too. So, you know.
Oh, my name?
Yeah, it's par for the course.
Okay. Goes here. Okay. Okay, so problem 3.8, I think. Sorry, can you guys hear me? I have my heater on, so it's kind of loud.
Yep.
Okay. Okay, so for 3.8, we just were asked to show that the direction of the frequency always moves in the same direction as the derivative of fitness, or average fitness, which is this equation 3.5. Okay, sorry, yeah, okay, so we have this equation for average fitness. So I guess the way I chose to do it, because it seemed the easiest, is just to work backwards. So if you take the delta P equation, you can just you can just take off this first factor and then look at the second thing, which is just dw dp. And then you take the derivative of w bar. So when you do that, yeah, it looks like they're like this. Basically, you just, what do you say? You take the derivative and then take the derivative of the inside thing type of thing. So you know dq dp is just going to be -1 because q is a function of p. So basically, you just work through each term and take derivatives. So the first thing would be 0. The second thing, you take the 2hs out, derivative of p1 times q, and then plus p times derivative of q, and so forth. And the last thing, minus, you drop the 2 down to q dq dt from calculus. And then you can basically just substitute in what you know dq dp is. and you end up with this thing, which happens to perfectly match that. So yeah.
So that was just a little bit of calculus that little bit of calculus creates an intuition for you. What it says first and foremost is that the change in allele frequency is proportional to the change in fitness. So that if fitness is increasing as you increase P will increase. If fitness is declining, when mean fitness, if mean fitness is increasing with respect to P's increase, P will increase. If mean fitness is declining with respect to P, P's frequency will decline. And the rate at which this happens is proportional to the slope of mean fitness, the variance in allele frequency, normalized by mean fitness. You may not have predicted this, but you shouldn't be surprised by it in retrospect. That the change in allele frequency is proportional to the change in population mean fitness, normalized by the variance in allele frequency and the mean. Does that make sense to everybody?
I'm sorry, could
So I
you?
guess in the text he did mention. Oops, sorry.
Yeah, go ahead.
I guess just in the text he mentioned that. Oh, sorry. I think I have a delay. Okay. Okay. Well, so he said this was like Fisher's fundamental theorem, but that in a lot of the cases what didn't really apply. So when we're looking at just like, I guess, stuff we would be working on research, should we assume it probably will apply or not, or is it just kind of like?
I think if you're working on a one locus, two allele system, it always applies. When you start thinking about more complex models of selection with multiple loci, you can almost, it's hard to even often articulate what you mean by it. That when you start thinking of the fitness surface as having many local minima and local maxima, it might be true locally, but not so true globally. And you can even find cases where it's not necessarily even true locally, depending on how perverse you're willing to make your model. But the take-home message is for a single locus, this is the way to think about it. But don't get yourself too wrapped around a pole as you generalize to more complex situations. Did you have a comment, Brooke? Is Brooke gone?
Nope, all good. Thanks.
Cool. Is everybody clear on this? This is an important thing in the sense of the intuition of allele frequency ought to change in the direction that maximizes population mean fitness. That intuition is a good one for you to have, and to always assume that's what's going on, barring extra information. But don't assume it is impossible to construct something sufficiently perverse that it wouldn't be true at. And you can probably find yourself into some weird, paradox worlds where you've constructed a model of selection that is totally weird and doesn't have this property. And if you assumed it did, you get yourself in trouble. But this is the right intuition in simple situations.
If you had like frequency dependent selection, would this not be the case?
Yeah, those are probably among the models we could start have perverse properties. Not a simple frequency dependence. Simple frequency dependence will behave in this fashion. But if you start getting these weirdo frequency dependence where you got one locus's frequency depending on another locus's frequency, depending on another locus's frequency, and they're selecting in opposite directions, maybe with and without linkage disequilibrium, you can get all sorts of nonsense going on. That if your name is Mark Feldman, you can like care about these models, but I have trouble caring about them. Other questions? Okay, up with the next problem is Mega.
I did these separately, but we just had to use different values of H. So for the first one, I got an upside down parabola. The second one, I got a straight line.
Let's what is our x-axis and what's our y-axis on this thing?
The x-axis is P versus W bar.
P versus W bar. So we probably only need to be looking at the 0 to 1 range on these things.
Okay.
Cool. Okay. So if P is going between 0 and 1, you have here W bar and it looks like it's always increasing from 0 to 1. And what value have we assumed here?
This one is 0.5.
Right. So any kind of incomplete dominance, additivity, suggests mean fitness is always increasing with P as P goes from 0 to 1. Cool. Excellent. What value do we got?
And this one was negative 0.5.
This. Let me take a look at
It
my.
looks like I wrote 0.5 again.
Yeah. Yeah. So one of them is. No. Oh, I see. Hold on. Maybe I'm going to actually share my screen because there may be a subtle thing going on.
Okay.
Let's see it here. So let me share mine. Just because you've plotted it completely correctly, but because of the scale, I think it's going to be hard to see the bit that you were supposed to see. So are you guys seeing my screen now with 3 plots? Can everybody see my screen?
Yep.
Yep. So when H is between 0 and 1, here is H as a half. Mean fitness is just increasing, a simple, basically linear function, increasing as a function of P. When P is very small, it goes from mean fitness of 0.9 to when P is very large, or mean fitness near 1. So it is just increasing, population mean fitness is increasing as P increases. However, when H is negative, this is over dominance. You may not be able to see it quite so well at my scale, but there's actually a peak here to meet population mean fitness. That peak occurs at H minus 1 over 2H minus 1, which I think here is probably something like 2/3 or something. And that's where population mean fitness peaks. It's at the equilibrium point when you have overdominance. When you have underdominance, population mean fitness takes a minimum at H minus 1 over 2H minus 1. So again, this is exactly equivalent to our delta P pictures. When H is between 0 and 1, delta P is just increasing the A1's frequency. When H is negative, the frequency of the A1 allele will increase if it is below the equilibrium, and it will decrease if it's above the equilibrium. And population mean fitness will increase in those directions. And here for underdominance, if somewhere around here is H minus 1 over 2H minus 1, the allele frequency will decrease when it's less than the equilibrium, and it will increase when it's greater than the equilibrium. So in all cases, we're going to be moving away from the equilibrium. Does that make sense to everybody? So these pictures of population mean fitness were teaching us nothing more than the same pictures for delta S, wherever those are. Those pictures, the delta P pictures, were showing us the exact same thing as the mean fitness pictures, really, at a fundamental level, because the fundamental theorem of natural selection. They are telling us the same thing. The change in delta P, the change in P, delta P, is proportional to the change in mean fitness with respect to P. Questions? Up next is Jim with the next problem.
All right. We're on 6, right?
We were on 6. Yeah.
So the question was, let the mutation rate from A1 to A2 be 10 to negative 5, and the fitnesses be these various fitnesses for each of the genotypes. What is the equilibrium frequency of the A2 allele? So I think the first step, because of an equation we were given for this in Gillespie, was to find H in this situation.
Mm-hmm.
And to do that, I think you have to find S as well. So we know each of these two things, 1 minus HS equals 0.99 based on this, and 1 minus S equals 0.98. You can solve for S and you get 0.02, and then you can put that in and solve for H in this equation. And H equals 0.5. And then with just a formula from Gillespie, he approximates the equivalent, the frequency of Q as U over HS. So that's 10 to negative 5 over 0.5 times 0.02, which I got is 0.001.
Absolutely perfect. Not only is this perfect, now let's see what's happened here. We've now added a new force. So as of problem 5, we are supposed to now understand what selection does. If H is anywhere between 0 and 1, what selection should do is drive the A2 allele frequency out of the population. Should make the A2 go away. There shall be no A2. That's it. It's gone. That's what selection will do. However, in this problem, we've now added a new force. That new force is one we've seen before. We're going to call it mutation. And every generation, an A1 allele is going to mutate to an A2 allele with a probability of 10 to the minus 5th. A2s never mutate to A1 because, well, whatever, it's the model. And so in this case, selection is driving the A2 allele out of the population, but mutation is adding it back constantly. And what Gillespie shows, or at least approximately shows, is that these two forces will eventually balance, and the rate at which A2 is being eliminated by selection will be balanced by the rate at which it's being added by mutation. And that balance of it being eliminated due to A2, eliminated due to selection, but added due to mutation, balances when the A2 frequency, Q hat, is approximately the mutation rate divided by the heterozygous selection difference, HS. 1 minus the heterozygote coefficient times the selection coefficient, whenever H is between 0 and 1. This approximation only holds between H is between 0 and 1, But if that's true, it should, the equilibrium frequency should look like the mutation rate divided by HS, which is a small number. But this, boys and girls, if you have any thought of being a human geneticist, is your default model. If you're interested in an allele that contributes to a disease, your back of the mind always, this is the model I think that's going on, is that the frequency of the disease allele is in mutation selection balance. That the alleles are being introduced by new mutation, they're being selected out by selection because they cause disease at some rate, and that their ultimate frequency is going to look like the mutation rate divided by HS, and HS will be relatively large if they have a large effect on disease, so that the equilibrium frequency will be a number that doesn't look like 0.1, that doesn't look like 0.01, but looks like a number much less than that. This is your intuition for most large effect disease alleles. It should always be your default model. If it has large effect, someone needs to give you a reason for believing its frequency isn't mutation selection balance. Convince me its frequency is bigger than 10 to the minus fifth. Go ahead. That should be what you think of when someone says, I'm going to tell you about a large effect disease allele. Your answer is, yeah, I know about it. It's 10 to the minus fifth, 10 to the minus sixth frequency. If it isn't that, there's got to be a weird reason. Does this make sense to everybody? Large effect things ought to be rare. They ought to be hanging out mutation selection balance, because selection is a strong force to drive them out of the population. And if they exist, they're probably being balanced by mutation. Everybody's clear? Taylor, up next with problem next. Here we are.
So we're on problem, I think, 7.
I think we are.
Okay, so we have a mutation rate from the A1 allele to the A2 allele of 2 times 10 to the negative 6. And we're assuming that the equilibrium frequency of the A2 allele Q hat is 0.002. And we're asked to find the fitness of the A1 to A2 heterozygote. So I'm using the same formula that we used for problem number 6. So Q hat is approximately equal to the mutation rate divided by H times S. We know the mutation rate is 2 times 10 to the negative 6, and that implies that HS is approximately equal to the mutation rate divided by Q hat, and that's 0.001. And so we know what HS is. We know that the relative fitness of the heterozygote is 1 minus HS. It's 1 minus 0.001, and that's 0.999.
Absolutely. Perfect. Absolutely perfect, sort of plug and chug. You can go any which way around. And although we did this, again, because, give you a little practice plugging and chugging, there's a good chance you're going to be asked to plug and chug like this on the exam in some fashion or another. But the real reason we gave you this is these are kind of realistic numbers. So if you think of the A1 allele as something like the perfectly healthy protein, and you think of a mutation rate as 2 times 10 to the minus 6, that might be the probability you get a mutation anywhere in the protein that damages it. If the fitness of a heterozygote with one broken allele is 0.999, almost 1, just 1/1000th away from one. So if we think that this is proportional to the number of children you have, if the average person has one child, the heterozygote has 0.999 children, hardly different than one. We still expect the frequency of these loss of function alleles to be 10 to the minus third. If they have even a speck of fitness effect on the heterozygote, we expect their frequency to really be quite low, unless their mutation rate is ridiculously high. These are sort of reasonable levels of mutation to expect in most organisms. So if it touches the heterozygote fitness, even 1 in 1,000, those alleles are going to be really low, really rare.
So I guess the thing here is that the frequency of A2 allele is not actually the frequency of one mutation. It's the sum of all the different mutations that impact fitness, right?
Exactly.
So individual one could be a lot smaller than that too, right? Like for any one mutation.
This is about the class of all the alleles that are affecting this gene at a level of 10 to the minus third in a heterozygote form. So if you are thinking this is something like all the alleles that you're throwing into your scat test, all of them together have frequency 10 to the minus third if they affect heterozygous fitness at 10 to the minus third. So you have no business including an allele at 1% frequency in your scat test unless you think HS is truly 0. You think this is a full-on recessive type thing. Or this thing doesn't affect fitness somehow, but affects your disease in a way that your disease doesn't cause people to have fewer kids. Maybe you're working on Alzheimer's or something. I don't know. Questions?
Can I ask a question?
Yeah.
So at what point would like a selective effect like this be like impossible to tell because there's other evolutionary forces like, drift or something like that that would be changing the frequency of that allele?
Yeah, we're right there. We are right there, right? So you know that that drift affects allele frequencies at something like with 1/2n. So if your population size effective is on the order of 10,000, the size of drift is remarkably close to the size of selection here. Maybe here selection is 10 times stronger than drift. But one order down, they're going to be the same kind of size. One order down from there, drift is going to dominate. So this is getting towards the sort of neutralist worldview that if most of these HSs are like 10 to the minus third, 10 to the minus fourth, 10 to the minus fifth, at some point, even though selection exists, if it's at 10 to the minus fifth and my population size is 10 to the fourth, I can formally and fundamentally ignore selection maybe, or at least approximately ignore it. And it's really going to only be when S times population size is of order 1 where it's confused. If N times S is very big, we can just think of it as selection. When NS is much smaller than 1, we can think of it as just drift. And of order 1 is where all the complications are going to happen. Questions? Up next is Christopher with maybe problem 8. I don't know. That's where they are.
All right. So this is, I think, just kind of a plug and chug and plot.
It is? Again, but we're going to build some intuition here, hopefully. Yeah. What a ugly,
That's-
boring graph that was. Walk us through.
Yeah. Yep. So, like I said, it's just kind of a plug and chug. So we know the allele frequency of cystic fibrosis is 0.04. Plug that into the equation, that simplifies out to H equals mu over 0.04. Plug that into the graph, and that's what you get. As mu increases over this range, H increases a slope of 0.04.
Yeah. So again, this is about trying to build our intuition. We imagine that for any genetic locus, the mutation rate per site per generation is probably on the order of 10 to the minus eighth. Maybe it's 2 times 10 to the minus eighth. Maybe it's 10 times 10 to the minus eighth. Maybe it's 0.1 times 10 to the minus eighth, but it's kind of in that range. So a gene has some number of bases in it. Maybe it's got 100, maybe it's got 1,000, maybe it's got 10,000, but not dramatically out of that range. So for any gene that that isn't all realistic, we imagine that any sort of moderately realistic allele frequency, mutation rates, anywhere for the gene, from 10 to the minus 7th to 10 to the minus 3rd, if the equilibrium frequency is as high as cystic fibrosis is in Northern European populations, as high as 4%, that's like huge for like a Mendelian disorder. It's one of the highest of any Mendelian disorders in the world. But if it's as high as 4%, that is still could be balanced by just the tiniest of selection coefficients on the heterozygote. If being a carrier for the delta F508 mutation, that one of the big causes of cystic fibrosis, if being a carrier for that mutation makes you 1% less fit, maybe 2% less fit than a homozygote, that'll explain the allele frequency for just about any value of any mutation rate for that locus that you could possibly believe. So tiny little bits of heterozygous disadvantage can perfectly well explain just about any allele frequency for a Mendelian disorder you've ever observed. You don't need to invoke any kind of crazy explanations other than the heterozygote probably has slightly less fitness than the most fit homozygote, but only slightly less. And that can explain a wide range of reasonable mutation rates for a wide range of Mendelian disorders. You don't need special argument to understand why any old allele frequency could be what it is. The only reason you'd ever need to resort to special argument is if you know the allele frequency is only that high in one population. If in most populations it isn't very high, then it is probably not mutation selection balance, but maybe there was something about that population that changed its frequency and its history, either selectively or due to drift in a small population. But if most places you look, it's at a low frequency, it's in mutation selection balance everywhere. Does that make sense?
So here, when we're talking about an impact to fitness for the, an individual who's heterozygous for this, cystic fibrosis, it's not necessarily doesn't mean that that person will have health issues. It's more that they might have potentially less children that survive.
Absolutely.
Right?
Yep.
Okay.
Or in this particular case, we can make up a little story, right? The cystic fibrosis allele tends to cause what does it do? It makes mucus in your lungs, right? Like when it's working properly. So if you have two alleles, you get a lot of mucus, you get sort of a nicely proper amount of mucus in your lungs. With one allele, maybe you get a little less. With two of them, you get almost none. So when you have two of these alleles, like you tend to die very young from infection in your lungs. When you have two functioning ones, well, you're however you are against lung disease. But maybe with only one allele, you're only 99% or 98% as likely to recover when you get tuberculosis or some other lung disease. Almost as good, but not quite. Does that make sense? Or maybe it actually, so Jim also may know, cystic fibrosis also has an effect on sperm function. And maybe all of this is actually about the number of offspring you have. It has nothing to do with your lung disease or lack thereof. But maybe a heterozygote has slightly less sperm motility, and people with a heterozygote have just 1 or 2 in 100 fewer kids on average. Questions? Up next is Zhangji with whatever problem is next. We're on 9, I think, ish.
I knew that was coming. So,
oh, you got a good one.
I don't think your random order generator is very random because it
totally
seems it's
random.
very predictable.
It is totally random. Part because I don't even look at it before. Although there's one random aspect that you guys may or may not figure out at some point. But
so if you think it's random, if you say it's random, then I'm going to guess that the next person after me is either going to be Michelle, Kiana, or Marisa.
It is Kiana, but there are only 4 people left in the. You've named. So there are only 4 names left, and you named 2 or 3 of them.
Okay, next time I will try to give the first person for the class. Next class. Let's see if it's random.
All right. I am using Perl's random number generator. So if it has if that has a known crack in it, I may be using, like, I could be using a cracked number generator for all I know.
Okay, so I think I'm doing 9.
9.
Yes, I realized that the previous few problems, since I was using a different edition of the book, I wasn't. The problems were scrambled, but it's the same problems. Yeah.
No, this one's correct.
Okay.
This problem, yeah, absolutely.
Okay, so problem number 9 is to derive the equilibrium frequency for A2 in terms of mu and s for this locus that has a fitness of 1 for the homozygous A1, 1 for the heterozygote, and 1 minus s for the homozygous A2. So the first line, this is from the book. Actually, I'm not sure you can see the mouse, but
nope, you can see it. It's perfect.
Okay. Oh, okay. So this one is from the book where we're under mutation selection balance, and so basically it's just some algebra. Since h is assumed to be 0, we can simplify this term over here, and this becomes p times q squared s over 1 minus sq squared. And if we set 2 sides, so mu times 1 minus q equals p times q squared s, where I replace p by 1 minus q, and I did some further algebra, we end up with q squared equals mu over s plus s times mu, and then we take the square root, and that's the equilibrium frequency.
Yeah. I would personally say mu times s is by definition at least 4 orders of magnitude smaller than s itself. So I would simply have written that mu over s square root, because s plus, 1 plus mu is very, very close to 1. And that is if you look up the formula on the internet for a recessive allele, that's the one they'll give you at equilibrium. This is I think Haldane probably derived this formula in 1918 or something. This derivation is just perfect. Does anybody have any questions? So again, all we've done is set the rate at which mutation enters the or rather mutation creates A2 alleles, set that equal to the rate at which selection gets rid of A2 alleles, and solve for what frequency of Q will those things balance out, and you get Q squared over S divided by 1 minus Q squared over S. And if we know that Q is going to be a small number, 1 minus Q squared over S is very close to the number 1. And many people would have jumped to the answer about 3 lines sooner, making the approximation 1 minus Q squared S is about 1, and called it good. But this is it. This is the intuition. So if the heterozygote really has no effect at all, we still expect the equilibrium allele frequency to look like the mutation rate divided by the selection coefficient square rooted. So if mu is on the order of 10 to the minus 6th, S is on the order of 1, the allele frequency is still going to be on the order of 10 to the minus 3rd. Maybe it could drift up to 10 to the minus 2nd, but not much bigger than that if S is large. Does this all make sense? All right, up next is, I think I previewed it, is Kiana.
All right. This one was like 2 pages of algebra for me.
Oh, yes, it is. It's going to be 2 pages
So
for everybody.
I'm going to do my best to explain it. But so basically where I started was we have an overdominant locus. And so when we have an overdominant locus, these 2 statements are true. The equilibrium frequency is P is given by this. I accidentally switched them while I was doing this algebra, but I don't think it changes the final answer at all. And we know that when there's overdominance, the heterozygote is the most fit genotype. So our max fitness is going to be the fitness of the heterozygote. So the genetic load formula is it's down here, W max minus W bar over W max. And so I first found what W bar is here. So we know that W bar is given by this formula, and we're solving for it at equilibrium. So P and Q become P hat and Q hat. We know what P hat is because of the fact that it's an overdominant locus. And we know what Q hat is because it's 1 minus P hat. So I plugged those in and I basically just did all the algebra. I got this expression for W bar and I plugged it into the genetic load equation. So the fitness of the heterozygote is going to be 1 minus HS. And so you have 1 minus HS minus W bar over 1 minus HS. Where W bar, I plugged in this using P hat for an overdominant locus. So when you do that, you get another page of algebra basically. And so I simplified it. I don't really know how else to explain that, but I basically went through and I tried to lastly get all the terms with S in them into one fraction and all the terms with H in them into another fraction. And This is the format of the final answer that I get. This HS over HS minus 1 times 1 minus H over 1 minus 2H. And then the interpretation of this. So the question was asking, I believe, is this genetic load, how does it compare to the genetic load for a population made up entirely of A1 homozygotes, for which there's no possibility even of an A2 allele? So basically, when you have a population of entirely A1 individuals, you have a genetic load of 0. Since your only genotype is the most fit genotype and also the average genotype, which is A1. So this is lower than the genetic load that I just derived for an overdominant locus at equilibrium. But also a population of entirely A1 individuals or A1 individuals also has a lower mean fitness than a population that has both alleles. So kind of how I interpreted this was that if A2 was to be introduced, the genetic load would increase as the mean fitness would be lower than the fitness of this novel, more fit A1, A2 heterozygote. So while the mean fitness of the population would increase and eventually reach an equilibrium, the genetic load would still be larger than 0 since there's another allele and not just A1. So I interpreted this as, in some cases, it seems like populations can deterministically move towards a higher genetic load in order to maximize fitness.
This is all just absolutely perfect. It's just algebra. And yes, that value there is p hat times something that is bigger than 1. So it's a number that is positive. So genetic load is an old concept introduced by Haldane, I think, probably originally. And every single generation of population geneticists at some point or another finds a brilliant member of their cohort that starts building models of genetic load and showing that under reasonable amounts of variation, the genetic load gets very, very large. And then they go and interpret that to mean something. And that's where it all goes wrong. Genetic load has a definition. It's the difference between the best possible genotype fitness and population mean fitness, normalized by population mean fitness or something. It doesn't mean anything other than that. And if you go and interpret it, be really careful. Because simple overdominance will make that value really big. And overdominance is good for the population. It's better to be at an intermediate allele frequency than it is to be at either all A1s or all A2s, because heterozygotes are the most fit. It's better to be heterozygotes. It's better to have genetic load than not. So if you made a population all of heterozygotes, like of overdominant loci, if that's your model of the world, everything is overdominant, your genetic load is really, 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 really big. So what? Your population mean fitness is being maximized at a value of genetic load that is unbelievably large numerically. It doesn't mean anything per se. The notion of genetic load, when sort of Haldane first introduced it, he was thinking about selection acting by way of a hammer. That he was thinking the way natural selection worked is certain genotypes got hit by a hammer and killed before they were allowed to reproduce. That's the way selection worked. It was hard selection prior to reproduction. So if the way selection works is it has to kill somebody, like a being in the population has to die in order for natural selection to work, then you might imagine that a large genetic load implies lots and lots of people are being hit by hammers. And the way most people will end up constructing these load arguments is they're imagining, can you make a population size big enough so that that number of people can get hit by a hammer and die before with selection work, and they wrap themselves up in little sort of crazy argument balls. But it turns out even those arguments don't really hold, because the definition of load is not, it's the difference between mean fitness and the maximal fitness, which in no sense necessarily has to be achieved. There is no reason the maximal possible fitness genotype for the population has to exist. So even if you think the way natural selection works is the way the world is people are being selected out of the population by being hit by a hammer so that they are no longer allowed to reproduce before, they're no longer allowed to reproduce. That the maximally fit genotype might be 10 orders of magnitude or 100 orders of magnitude more fit than the average doesn't mean anything unless that genotype has any probability of existing. And you can show for any of these models where you make some sort of natural model of selection, where even if selection is acting by hitting people with hammers, you can show that the maximally fit genotype is astonishingly unlikely to exist. So any intuition about what the size of load means it's just not a very interesting concept. We are teaching you about genetic load for two reasons. First, so you know how it's defined and so that you can calculate it yourself if you really want to. So you take my caution that you don't make these load models and try to overinterpret them. But if you do have an experimental system where you can make genetic load be a meaningful concept, maybe we can actually make some interesting inferences using ideas from genetic load arguments, as we will see in the Greenberg and Crow experiment. So there are a few very, very artificial systems where this concept in particular will turn out to be insanely powerful. But I can hardly think of any other place where it matters. All right, a bunch of terrible algebra. Brooke, you're up next with the next problem.
Cool. This one I had a couple leaps of faith on, but we shall see. All right. Oh, okay. Okay, sorry for it being a little bit fuzzy on here.
Oh, this one.
Yeah.
Right.
Oop, that's worse. I should zoom out a little bit. 1 second. I'll make it 100. Okay, so the question was about if you have a single second locus or a single second chromosome, and it has 20% of the loci in the haploid genome have I think it's the lethal mutation, or like a lethal mutation. And then the goal was to calculate the probability that an individual as a whole will be completely free of the lethal mutations. So basically the way I kind of had to reason it out, because I didn't quite get it at first, but you needed some information, I think, from the preceding paragraph. I think this is question 3.13. Is that right? Something like that. But basically, kind of how I set this up was 23% of all the genes were lethal on the second chromosome. So it's not the 20% here. So those that are not lethal on the entire second chromosome are going to be 1 minus 0.23 or 77% of the genes when you have this homozygous A1 situation. So then how I kind of was trying to figure it out was you have this certain number of total loci, which I represented as X, and we're trying to look for P, which is also 1 minus Q. And I've set it equal to 0.77 because we know that this is the not lethal version. But we know that just for the second chromosome, we have it at this 0.2 value, or we have 20% of all of these loci. So then I think with just like a little bit more trying to figure out the logic and trying to understand that we're looking at this in terms of our homozygous pairing. So it's got to be for the whole individual, not for just the second chromosome. We also need to look at it as we have a diploid individual. So we have 2X. And so when I kind of figured that out, it was basically just a way to get rid of our X term so we could actually solve for something. And so you have this value of 10. And when you actually start to break it down, you can start to solve for the value of P, which is 0.073. But then I subtracted this P from 1 to get 0.926. It was a little bit of a jumbled logic that I had to try to put together in my brain, but this is what I got.
So something that's a little funny about this. So do I quite get this right? I think so. This is close anyway. So remind me what Q is here again?
So I think I set this up so that Q would be, hold on, I gotta think about this too. Because I kept switching it back and forth as I was trying to write it out. So 1 minus point, so I think I may have flipped it around and made Q, instead of it being the lethal, it's the not lethal form, or like the A1, I guess. I accidentally made Q, or because what I've done is I've said, yeah, no, okay. Q is the lethal, and I tried to set everything. No, I flipped it around. I made it backwards.
Yeah. So let me share. This is more or less right on. But let me I'll share mine. So the first thing to say too is Gillespie's problem is extraordinarily confused in its statement / in the results. The stuff isn't, if you didn't think what he wrote quite made sense, it's because it's kind of wrong. So let's start from the beginning here. If you looked at his answer rather than looking at your own, or even you looked at the stupid words in his problem. So where am I? Come on. So we're on problem 12. So if there is any Drosophilist in the room, the first thing you know is the whole premise of the problem is stupidly phrased. The second chromosome, 1 second chromosome is 40% of the haploid genome. 2 second chromosomes are 40% of the diploid genome. The fly is basically, it has one arm that's X, two arms that is second, and two arms that is third. So you sort of think of the fly genome as being composed of sort of 2/5 second chromosome, 2/5 third chromosome, 1/5 X. So so the second chromosome is 40% of the haploid genome, or it's 40% of the diploid genome. Either way around you sort of want to put it, but it's at one second chromosome is 20% of the diploid genome, 40% of the haploid genome. The number of loci on 4 and Y are negligible. So let's just get this logic down like clean from the beginning. So the problem postulates that the second is 20% of the diploid genome, 40% of the haploid genome. Thus, the total number of loci in the diploid genome of the fly is something like 5 times the number of loci on the second chromosome. I'm going to call the number of loci on the second chromosome M, and I'm going to call the total number of loci in the genome is 5M. If we assume that loci are all independent and they all have about the same probability of adding a lethal allele, and we're going to call L the probability that it is lethal, and 1 minus L is the probability that it's lethal free, the probability that the second chromosome is lethal free is something like 1 minus L, the probability any locus is lethal free, raised to the M, the number of loci on the second chromosome. And the text tells us 1 minus L raised to the M is equal to 0.77. So the question asks, what's the probability that the entire genome is lethal free? So 1 minus L is the probability any locus is lethal free. The total number of loci is 5M. The text gives us 1 minus L to the M is equal to 0.77. So the total probability the entire genome is lethal free looks like 0.77 raised to the 5th, or 0.27%. And your answer and mine differ simply by a factor of 2 here, where you have a 10 where mine is a 5, giving you a number like 7% rather than 27%, because I use the actual percentages in the genome rather than the thing Gillespie suggested. Does this make sense to everyone? So the way to think about the problem is to try to make a concrete model in your mind of some number of fixed loci. We're going to call those loci M, is the number of loci on the second chromosome, and we're going to call 5M the number of loci on the whole genome, and then we're going to take sort of averages.
How did you know that the total number of loci was 5M? Like, where did you get the 5 from? Because of the 20%, 40%, 40%?
Mm-hmm. Okay. That's it. If M is the number of loci on one chromosome, and that is 20% of the whole genome, total number of loci is 5. No, that's it. So M is the number on a single chromosome. That is 20% of the genome. So the whole genome is 5 times that. Yeah, this problem is seriously confused, in part because Gillespie's original edition of the book got the proportion of the genome correct, but his answer was wrong. And then when he corrected it so that the proportion of the genome was wrong, but it matched his answer. And so the answer, I believe, is correct for the numbers he gives, but the numbers he gives are wrong and don't match reality. So it's all just very confused. Up next is Julie with problem next, whenever. We are backing our way into Greenberg and Crow. In fact, no, we are going to, never mind, Julie. Julie, you're going to do this problem first next time.
Okay.
I think you're going to start with this problem next time. And God, I've never goddamn done this without a blackboard. Let's see. I think I have the same bootleg copy of Gillespie that you guys do. Let me see if I can find it. So, documents, courses. Sorry, I wasn't prepared. PopGen. Yeah, this is bootleg copy that you guys have. Greenberg and Crow. Yeah. Oh, gee whiz. Oh, no, it's there. Good. Okay. Share screen. So the next problem, and the next maybe even couple problems, is going to talk about this Greenberg and Crow experiment that's not so well known, but is really, really interesting, and something that the results are so clean and so nice that they imply some really sort of powerful ideas. But we're first going to just talk about the experiment. So the first thing to know about Drosophila is there are an enormous number of tools to manipulate the fly genome. And included among the tools are these things that are called balancer chromosomes that have multiple inversions along them. And because they have multiple inversions along them, they are incapable of recombining in any sort of sensible way. And many of these balancers are marked in a way so that you can see whether the fly has that chromosome by eye from a distance. So they will have a funny color or a funny looking eye. And you will know right away whether the fly has this balance, has a copy of these balancer chromosomes. So you can do these experiments where you take a fly from nature that has two copies of, say, a second chromosome, any old second chromosome found in nature, cross it to a fly that has two balancer chromosomes on chromosome 2, say, or 1, or X. They're balancers for all of the major Drosophila chromosomes. And from here, you'll get F1s that have a copy of a chromosome found in nature and a balancer chromosome. And you can cross them again with sort of double balancers and end up with chromosomes that are fully intact and opposite balancers. And then you can intercross these and get individuals who are sort of fully intact homozygotes, and by combining different lines, individuals who are two different chromosomes taken from nature. So these individuals are homozygous for a single X chromosome. Other individuals are homozygous in the sense that they have no balancers, but are heterozygous for two different chromosomes found in nature. And then you can have these sort of individuals that are heterozygous over balancer alleles. And we can talk about, if we grow a lot of flies, say the number of individuals that are outbred, these are just two random chromosomes taken from nature, versus people who are fully inbred for chromosome 2 versus balancers. And what you find is, if we normalize everything to the sort of viability of these one of a second chromosome in nature opposite a balancer, individuals who are outbred, meaning 2 second chromosomes picked from nature, tend to have sort of viability of 1 on average. Some of them have more sort of viable offspring. Others have less, but it looks like a normal distribution, more or less, normalized to 1. On the other hand, inbred individuals, these are individuals that have a second chromosome fully inbred. Some of these guys are just dead. Some of these lines are dead, dead, dead. There are nothing coming out of them. On the other hand, others of these second chromosomes have a viability that is not equal to outbred individuals. It has a mean smaller than that, but not dramatically smaller than that. So Greenberg and Crow's interpretation of people who are fully homozygous for chromosome 2, this is made up of 2 classes of alleles. Alleles that are homozygous lethals, these just kill you, and alleles that, while not lethal, are in fact of reduced viability relative to the homozygous class. So these sort of fully inbred individuals look like some chromosomes have homozygous lethals, and other chromosomes have alleles that are deleterious in homozygous form relative to outbred alleles, but only somewhat. Is this making sense so far? So, and how we calculate these curves are exactly how you think. You count the number of flies that came out of like a homozygous cross, and versus the number of flies that came out of some other the sort of controls. So, what are we going to do? We're going to assume that most loci are sitting around in Hardy-Weinberg, p squared, 2pq, q squared. We're going to assume the fitness of one of the genotypes, A1, is p. The fitness of the less fit homozygote is 1 minus s. The fitness of the heterozygote is 1 minus s. In outbred individuals, we just got Hardy-Weinberg, p squared, 2pq, q squared. But those inbred individuals are all homozygotes. They're all either A1 or they're all A2. And the probability that they were a homozygote for A1, is just its frequency. Probability that they were a homozygote for the other class is Q. So we imagine the mean fitness of a population of outbred individuals is something like 1 minus 2pqhs minus q squared s. That is the formula we've been using for just an outbred population, because it's 1 times p squared. You guys know where that came from. But these inbred flies ought to have mean fitness p times 1 plus 0 times 1 minus hs plus q times 1 minus s, which is the value 1 minus qs. So the first thing we learned from this experiment, because inbred flies have a lower mean than outbred flies, is that 1 minus this number, the mean fitness of a homozygote. This is the mean fitness of, a mean fitness of an outbred individual. This is the mean fitness of an inbred homozygous individual. If you do a tiny bit of algebra, you can immediately prove that H is less than a half. This picture that homozygotes have a lower fitness on average than heterozygotes for the second chromosome, outbred individuals. They're not really heterozygotes. They just have the possibility of being heterozygous. They're outbred. That if outbred individuals have higher mean fitness than inbred individuals, you have proven that H is less than a half. And it is. It's less than a half in this experiment, and it's less than a half in almost any experiment you will ever do in your entire life. Inbred individuals have on average lower fitness than outbred individuals, which is a proof that H is less than a half. It fits with your intuition. You've all sort of probably, at some point or another, you are probably taught, don't breed with your sibling because the fitness of the offspring is likely to be less than your own. It might have been put in a slightly less formal manner, but you were probably taught that at some point or another. It is almost always true in almost all organisms. And the implication of that is H is less than a half at most loci in nature. It's a powerful result. Very powerful. The next thing we're going to do with this Greenberg and Crow data is, for all the world, it looks like we have two classes of second chromosomes. It looks like some second chromosomes carry lethal alleles. Other second chromosomes carry deleterious alleles that are deleterious relative to outbred, but not really lethal. So we're going to imagine that the second chromosome is constructed of loci that bear lethal alleles. And we're going to say the frequency of those lethal alleles is Q, or at least the frequency of lethal alleles at the ith locus is QI, where I'm going to write Q as a big Q. It's a big Q because these things have big effect. They're lethal, they're bad. Big letters are going to refer to big fitness effects. Little letters are going to refer to little fitness effects. So at any particular locus, the probability that you are in this inbred population, in the inbred flies, you have some probability, 1 minus Q little I minus Q big I, of being a homozygote for a decent allele, probability QI of being a homozygote for a deleterious allele, and probability QI of being a homozygote for a lethal allele. For lethal alleles, we'll imagine the selection coefficient is like 1. That's what lethal means. And for the deleterious alleles, S is bigger than 0, but nowhere near 1. It's much less than 1. It's small. It's not near 0. It's bigger than 0, but it's much closer to 0 than it is 1. Does this all make sense to everyone? So from the picture, the average viability of outbred flies was almost 1. We're going to call the average viability of outbred flies is A. The relative viability of inbred flies, the mean of inbred flies, we're going to call B. And it turned out to be 0.63. other people have done the same experiment in flies, and they've always found values of B that are sort of in that neighborhood. And the average relative viability of an inbred fly without any lethal mutations we'll call C, and that turned out to be about 0.85. And other people have measured this, and then again, in flies, you almost always get values in that range. So,
Sorry, just really quickly before you move on, just with that table again, the phenotypes with the A2D and the A2L.
yes.
What were those? What was the difference between those?
So
again?
these are inbred flies. So the fly is necessarily going to be homozygous.
Mm-hmm.
At any particular locus, we'll say the ith locus, that fly might have been homozygote for a perfectly good allele that I'm going to call A1A1. Or he might have been homozygous for an allele that I'm going to call deleterious, meaning it harms the fly's fitness, but not very much.
Okay.
So here the fitness is going to be 1. Here the fitness is going to be 1 minus little si, where I make it little, make the si little because the fitness effect is little. It's not 0, but it's little. And I'm going to call the frequency of these deleterious alleles at this locus qi. Or they might have been homozygous for a lethal mutation. And a lethal mutation means its fitness is 1 minus s, which is very close to 0. So a lethal allele has selection coefficient near 1. And I'm going to write its frequency as also q, but I'm going to make it a big Q to remind myself that I'm talking about lethal things with big selection coefficients. So an inbred fly is either homozygous for a good allele, homozygous for a deleterious allele, or homozygous for a lethal allele. And that's what we're seeing in this picture. Outbred individuals are fine. This peak is being shifted back because so many flies are homozygous for deleterious alleles. This peak is being shifted back because they're homozygous for lethals. Make sense?
Yes, thank you.
Yep. And which is why, of course, you can see plenty of flies have viability that's great. That's right up there with outbred individuals, because these are the flies that effectively have very few deleterious and no lethals with them. But those are the chromosomes, if we want to be precise. So A is the fitness of outbred individuals. B is the mean over all inbred flies. And C is the mean over all inbred flies, excluding the lethal tail, excluding these things. It's really that kind. It's sort of the mean over that part of the distribution. All right. So here is sort of a fundamental genetic load argument. We're going to imagine that the reason these flies have lower fitness is because they are dying as maggots before they grow up to be perfectly good flies that are able to breed. That the way selection is acting here among these lethal and deleterious alleles is it's killing maggots dead. And if that's true, then we imagine the mean fitness of inbred flies is going to look like the mean fitness of outbred flies times the probability. So okay, so what is this? This is looking something like what 1 minus, this is the frequency of the lethal alleles at the ith locus. This is how bad a lethal allele is. So it's very close to 1, we imagine. This is the frequency of a deleterious allele at the ith locus. This is how much fitness you're lost from being a deleterious locus. So we imagine the mean fitness of these inbred flies is something like the mean fitness of the outbred fly times the amount of fitness it loses if it has a deleterious allele times the amount of fitness it loses if it has a lethal allele multiplied over all loci. That the way these loci interact is sort of independently and multiplicatively between loci, because these are fitness effects that are killing you. So it's something like, this is something like the probability of living from even though there might have been a deleterious allele, something like the probability of living, even though there might have been a lethal allele, multiplied over all loci. You have to live from all the deleterious sites. You have to live from all the lethal alleles, and therefore the overall mean fitness looks like outbred times that. Now, I already have values for A and B. So just to sort of make some of this go a little easier, we're going to take this product and maybe raise it to the E power and start getting things that look like sums rather than products. In fact, we're probably going to take E to the ln of this and note that that the ln of 1 plus x is about equal to x. It's a little trick you guys saw earlier. And we're going to approximate this probability as something like e to the minus sums, because we've gotten rid of our ln's in our head. And one of those sums is the frequency of a deleterious allele times its selection coefficient, summed over all loci. Here is the frequency of lethals times the selection against lethals. We're going to call these values loads because they really are genetic loads. This is the amount of fitness lost from all the deleterious alleles. This is the amount of fitness lost from all the lethal alleles. And now like this is all just a little bit of algebra. So D plus L equals the ln of A minus the ln of B. It equals that. Whatever. Now, that thing C, we will recall that C is the mean of inbred individuals who have no lethal alleles. So that value C ought to be the fitness of outbred individuals times the probability you don't die from having a deleterious allele at any of your n loci. We get rid of that lethal term because we know these people don't have lethal alleles. So C ought to equal that thing. And this is we defined above as the deleterious load. Take some logarithms, and we now can find D and L. So D, remind ourselves, is the frequency of deleterious alleles times their selection coefficient, summed over all loci. L is the frequency of lethal alleles times their selection coefficient, summed over all loci. And we get that ratio of D to L is something like 0.627. So the amount of fitness lost from being deleterious, it looks like it's about 2/3 what it is from being lethal. That these lethals are causing, sort of 1/3 more problem to the flies than all the deleterious ones. And there we go. Why have I done all that? So remember, these things, these Qs ought to be in mutation selection balance. So these little Qs ought to look like Ui over HS. These big Qs ought to look like Ui over HS. So if I plug in U over HS for this value, I get the sum of the mutation rate to, I get this ratio, D over L. Looks like the sum of the mutation rates to deleterious alleles divided by the heterozygous effect of deleterious alleles over the sum of the mutation rate to lethal alleles over the heterozygote effect of lethal alleles. That's just plugging in mu over HS. I've done nothing but plug in mu over HS and simplify. Don't look at this. But D over L ought to be little ui over hi, or divided by big ui over hi. Now we're going to ask something. Imagine for the moment little hi and big hi were the same value. They were on average both a half, or they were both little numbers, or they were both big numbers, but they were close to each other. If the h's were close to each other, this D over L ratio is nothing more than the ratio of their mutation rates. So it turns out that we have been measuring the ratio of mutation. We've been measuring mutation rates in flies since Muller's time in the 20s, spontaneous mutation rates. And Mukai did these beautiful experiments in the 50s measuring mutation rates. And we know for a fact from Mukai that the ratio of deleterious mutations to lethal mutations is way bigger than 1. Most mutations are not lethal. That maybe 2 or 3 times as many mutations are bad for flies as there are lethals. The D over L ratio we got was 0.6. The ratio of mutation rates is like 2 or 3 or 4. So we can conclude right now that this deleterious to lethal load being less than 1 proves that the HIs are not the same at deleterious loci as they are and at lethal loci. These H's must on average be different from one another, because otherwise this D over L ratio would be closer to 2 or 3. Let's imagine a different hypothesis, in one that's a little weirder. Let's imagine HS is always the same number. That if S is a big number, H will be close to 0. And if S is a little number, H will be close to a half. Less than a half, but close to a half. Let's imagine for the moment that HS is always about the same value, and it's always small. Let's just pretend. What happens? Well, if that number is the same, we can cancel it from the top, we can cancel it from the bottom. And this D over L ratio becomes the mutation rate to deleterious alleles times the effect of a deleterious allele, divided by the mutation rate to a lethal allele times the selection effect of a lethal allele. It also turns out that Mukai has been measuring that value over and over again. He hasn't been just measuring the mutation rates, but he's been measuring the mutation rate times the selection coefficient. for both deleterious and lethal alleles. And that value is somewhere in the range of 0.7 to 0.6 in experimental treatments. All righty. So we started with measuring the fitnesses of inbred and outbred fly chromosomes, got to a ratio of the frequency and nature of deleterious alleles times their selection coefficient, summed over all loci, divided by the frequency of lethal alleles times their selection coefficient, summed over all loci, that number being 2/3-ish. And if we assume HS is about the same, the heterozygous selection is about the same regardless of the size of S, that value should just equal the mutation rate times the selection coefficient summed over all loci. And that value ought to be in the range of about 2/3. Well, that sounds like an argument that HS is probably close to the same number, regardless of whether the allele has a very, very large effect, S being close to 1, in which case H would have to be a tiny number, or S is a tiny number, in which case H will have to be big, but on average less than a half, because we know H has to be less than a half from the first conclusions. There we will stop for today, and we will re-continue this homework with Julie doing the next problem, trying to develop some quantitative intuition about how heterozygous effects are related to selection coefficients. What kind of sort of relationships are consistent with this effect? Questions? All right. I'll see you guys on Thursday when we'll finish off these problems and try to develop the intuition which we will need the rest of our lives about what we expect to see from a heterozygote as a function of the behavior of homozygotes. See you guys Thursday.